This is the video on half-angle identities as well as sum and product identities. First I'll derive the three half-angle identities. So last time we had double angle identities, and we're going to use the one for cosine to derive the next three. So this is the one version of cosine 2a. If I now solve for cosine of a, I get this, and then I take the square root of both sides, and I'm going to switch sides now. I get this. Now if I let a equals 1/2 x, my end result looks like this. So now I have a half-angle identity. Cosine of 1/2 x equals this. Now the plus or minus actually will not be in your final expression, and you'll see why later. But for now, I'll just leave it there. Now I need to derive sine of 1/2 x. So to do that, I'm going to start with cosine 2a again, but I'm not going to use this identity. I'm going to use one of the other two. That one. And again, I'm going to solve for sine of a this time, sine of a. Now I'm going to let a equal 1/2 x like before. Okay, I'm going to get rid of this pesky negative sign by distributing it. That should have been an x up there. It's probably better to write this as 1 plus cosine x over here, just so there's some sort of parallel structure here, and you can see the distinct difference, which is the plus here and the minus there. Okay, so there's cosine 1/2 x, sine 1/2 x. Again, I'll explain the plus or minus later. So tan 1/2 x, as you might expect, you just take this one and put it over this one. So to make things go a little quicker, you'll see that the square root of 1/2s are going to cancel each other out. So I'm just going to get square root of still plus or minus 1 minus cosine of x over 1 plus cosine of x. Okay, so that's one way to express the tan of 1/2 x. We normally don't use this one though, because this can be simplified. So I'm going to multiply the top and the bottom here by 1 minus cosine x, because I'm going to rationalize the denominator. So the top becomes 1 minus cosine x squared. The bottom becomes 1 minus cosine squared x, which becomes sine squared of x, which when you take the square root just becomes sine. So rad's gone on the bottom, and the top, that's obviously just 1 minus cosine x. So it becomes this. However, there's no more plus or minus here. And I'll save that for later, the explanation of why that is. Now, again, taking this, I can multiply by something different, not this, to get still another equivalent expression that is just as useful as this one. So instead of multiplying by 1 minus cosine x over 1 minus cosine x, I'm going to rationalize the numerator, not the denominator. Probably never thought someone would say rationalize the numerator, not the denominator, but that's what I'm going to do. So I'm multiplying this fraction by this fraction in the rad. So we get, again, plus or minus. The top is going to be sine squared x. Bottom is 1 plus cosine x squared. So the top becomes sine of x, bottom 1 plus cosine of x. So these two are the most often used versions of tan of 1/2 x. And again, the plus or minus does disappear. And I'll save that for later. Okay, so what do we use the 1/2 x, half-angle identity for? This is an example. So let's say you're given an angle, or you're given a cosine of an angle, 3/5. Now that angle could be in quadrant 1 or 4. So you need some more information about this angle. Okay, here's the extra information. It is in quadrant 4. Okay, now that you have the quadrant pinned down, you have enough information to find sine of 1/2 x, cosine 1/2 x, and tan 1/2 x. Okay, first let's draw where this angle is. So it's in quadrant 4. The cosine is 3/5. So this is 3, this is 5, and this is 4. Okay, so sine of 1/2 x according to the identity, plus or minus 1/2 times 1 minus cosine of x. Okay, now I'm going to explain the plus or minus. So you're given that x is right there. So the angle x is that. But you're asked to find the sine of 1/2 of that angle. Okay, so if the angle is somewhere in quadrant 4, that means from 270 to 360, and we're only finding the sine of half of that angle. That means half of 270. So the minimum would be 135. And then the max would be half of 360, which is 180. So whatever one half of whatever 1/2 of x actually is, it is going to be here in quadrant 2. And quadrant 2 only has positive sign values. So I can get rid of this plus or minus now, because I am certain that whatever sine of 1/2 x is, it is positive. So that's why the plus or minus was in the identity up here and here. But once you are told where x is, there should be no doubt what quadrant 1/2 x is, and therefore no doubt whether the sine or cosine is positive or negative. So you should be able to figure that out. Okay, so proceeding with the calculation, rad 1/2 1 minus the given cosine, which was 3/5. And that is rad of 1/2 times 2/5, so that's rad of 1/5, which is rad 5 over 5 if we're going to rationalize. Okay, now cosine of 1/2 x. Okay, let's take care of the sine first. So we just determined that the half of this given angle is in quadrant 2, and the cosine in quadrant 2 is always negative. So this time we've got a negative sign before the rad. Okay, and then the only difference is I'm adding the cosine. So it's rad of 1/2 1 plus 3/5 this time. And that is 8/5. 1/2 times 8/5 is 4/5, so it's rad 2 over negative 2 over rad 5, so negative 2 rad 5 over 5 after rationalization. Okay, and then finally tan of 1/2 x. I don't think it really matters which one I use here. Yeah, it shouldn't matter. I'll just use this one here, the first one. So 1 minus cosine x over sine x. So the cosine's 3/5, 1 minus 3/5 over the sine, which is negative 4/5. So it's 2/5 times negative 5/4 or negative 1/2. And just checking to make sure, is the tangent of 1/2 x supposed to be negative? Okay, we're in quadrant 2, remember, and the tan there is negative, so that's correct. So the reason that plus or minus sign goes away is because once you have tan of 1/2 x in this form or this form, everything takes care of itself, including the sine. The sine takes care of itself. Because if you look at this expression, when you can just do it by cases, this case was a fourth quadrant angle, and a fourth quadrant angle will have a positive sine value, but less than 1, and a negative sine value. So it's a positive over negative, which will end up negative, which is what it's supposed to end up. And if you do other cases with angles in different quadrants, you'll see it just takes care of itself. So that's why in the derivation the plus or minus goes away, here and here. Okay, now we move on to sum and product identities. Most people consider this group of identities their least favorite, including me. And that's because they're long, kind of hard to memorize. But the derivation is easy to understand, so memorization is not really necessary. Okay, so if I take two identities we already know, the sum identity, sine of a sum, sorry, and sine of a difference, and add these two equations, the right side will simplify a bit because this plus this is 0. And these two are the same, two of the same, so I get that. So this tells me that if I have a sum of two sines, I can express it as a product in terms of A and B, the two angles that I had the sum and difference of. Okay, but the main idea is I can express a sum as a product, or a product as a sum, and that's the key. That's the key value of these identities. Using the same method, I can find out that sine of A plus B minus sine of A minus B. If I'm using the same two identities, I'm just going to subtract here instead of add. I won't do all the work, but you would end up with that. Okay, so that's the first, that's the second, and then the third you would get by using two different identities from two groups ago. And if I add them, I get the third one. And using these two again, but subtracting, I'll get the fourth. Okay, so since these four are so similar, that makes them a little hard to, for me at least, memorize. But you can see the derivation. It comes from the composites that were derived earlier, which by now should be memorized, and you just add or subtract two of them, and you can get these sum and product identities. And again, the key is you can now write a sum as a product, or a product as a sum. So here are a couple of examples where that comes in handy. So here I have a product, and I want to express it as a sum. Okay, so if I look at the structure here, I have 2 cosine A sine B in my product. Okay, so you just go to the one that fits. That would be this one up here, number 2. So to write it as a sum, you would write it like that. And A is 73 and B is 62. So 73 plus 62, 135, minus sine of 73 minus 62, 11. There. It is now written as a sum. Okay, so once you have these identities down, the practical problems that utilize them are really simple. Okay, now I have a sum and I'm trying to write it as a product. Okay, so remember in the sums, the arguments themselves are themselves sums or differences. Okay, so you need to find what A and B are, because 56 is A plus B, and 24 is A minus B. Okay, so you can do mental math or do a little bit of solving a system of two equations if you like, and find that A is 40 and B is 16. Okay, so once you know A and B, just find the right identity. There it is. So negative 2 sine 40 sine 16. And there you are. Sum written as a product. Okay, and then of course, as with all identities, you can use these to prove other identities as an exercise. Okay, so there are your half-angle identities and your sum and product identities. See you later.